Okay, got that going. All right, so started talking about derivatives last time. We did some basic proof rules. We proved the product rule, the quotient rule, and we figured out how to solve it when we're dealing with functions x to any integer, like -9, for example, right? And we also talked about even if it's multiplied by a constant, we still know how to deal with that. Remember those? Okay. So now today we're going to introduce two more derivative rules. We're going to learn how to take the derivative of an inverse function, and then we're going to learn how to deal with the derivative of a composition of two functions. So those are the two big ideas we're going to handle today. I think the composition one's pretty straightforward. I think the only trick today is going to be wrapping our head around the derivative of the inverse of a function. And the hard part about this is always just like keeping in your mind what exactly the inverse function is, I think. I think it's easy to lose track of what exactly the inverse function is. So, let's see, why did I want to know that? If f from I to r is strictly monotone, then f inverse from f of I to r is continuous. I'm guessing that I'm going to make reference to that in proofs over here. I'm not saying off the top of my head, but I don't care about that now. But let's establish our intuition for what exactly the inverse function is, and now what we expect the derivative of an inverse function to be. Remember our intuition for what a derivative is. It's the slope of a function at a point. That's the derivative of the function at the point, right? So we said if we've got some function here, y equals f of x, and if we go to some point x naught, y naught, there's the point. Then we said the derivative of that point is going to be its slope. And we said you can approximate the slope using the difference quotient, right? So far so good? So now think about what the inverse function is. You know what the inverse function does? It swaps all your x's and your y's. And when you swap your x's and your y's, the resulting function is the inverse function. Another way to think about it is if we swap our axes, then what we're left with is the inverse function. So here's the exact same function. Now here's my x-axis, here's my y-axis, drew the exact same function. But now, instead of looking at the slope at x naught, we're going to look at the slope at y naught. Notice we're still making reference to the exact same point, x naught, y naught, x naught, y naught. But instead of viewing it as y in terms of x, we're now viewing it as x in terms of y. We're looking at the inverse function. X is equal to f inverse of y. With me? Okay. So now, what is the slope of this line going through that point? Well, instead of it being the change in y over change in x, it's now the change in x over change in y. Right? And notice that this is just a reciprocal of that. So this slope should be the reciprocal of this slope, or 1 over that slope. And that is our expectation. Does that appeal to intuition? Okay. So we expect f prime of x naught to, if f prime of x naught is equal to m1, then we expect f inverse prime at y naught, m2, to be 1 over m1. So let's do some examples, a concrete example real quick to wrap our heads around this. So let's look at the function f of x is equal to 2x plus 1. And let's find the inverse function. Now you've been finding inverse functions, I don't know when you first start doing it, but we like to write this as y is equal to 2x plus 1, right? And now we're going to solve for x. So if y is equal to 2x plus 1, then that gives us that when we solve for x, we're going to get x is equal to y minus 1 all over 2, or in other words, x is equal to negative 1/2 minus, or plus 1/2 y. Did I do that right? Mm-hmm. So, another way that we can say that is f inverse of y is equal to negative 1/2 plus 1/2 y. If f of x is equal to 2x plus 1, then f inverse of y is equal to negative 1/2 plus 1/2 y. Notice, what's the slope of this function anywhere? 2. What's the slope of this function anywhere? 1/2. Oh, I don't know why I did the constant first. Oops. 1/2 y minus 1/2. There we go.
So
Your
for
mx plus b formula. So yeah, in this case it worked. Let's use a more complicated example and try it again. So consider this function, and let's look at, let's not use 6, let's use 3, a smaller number. So let's look at x naught at 3. If x naught is 3, we need to make a point. We need to keep in our minds what y naught is. At x naught 3, what would y naught at that point be? 9. Y naught equal to 9. Okay, so we know that f prime at, well, first let's find f prime of x. F prime of x is equal to what?
square root of x?
No, f prime. What's the derivative?
Oh, the derivative.
Oh. Just x? Or 2x, sorry.
2x.
Oh, we proved that already.
Yeah, real simple. Just subtract 1 from the exponent, bring down the exponent, subtract 1. That's equal to 2x. So then f prime at x naught, or 3, is equal to what?
6.
Just 6. So we better find that f inverse prime at y naught is equal to what?
F inverse prime at y naught?
Uh-huh.
It should be 1/6.
1/6.
Oh.
That's what we better find. So let's check that. So what is, maybe we should write this, what is f inverse of y equal to?
The square root of y?
The square root of y. Or y to the 1/2, right?
Yeah.
We know the inverse of that function. By definition, the inverse of that function is what this symbol means, x to the 1/2. Of course, we're going to use y's for our inverse functions. That way you can always think about as x mapping to y's to help keep it straight in your head. I know some books, when they find the inverse of a function, they like to write it both in terms of x. I think that can just get confusing, because then when you have an arbitrary x somewhere, you don't remember which function came from. So we'll be consistent, making, if f of x is equal to y, then we'll write f inverse of y is equal to x. Anyways, so now let's find the derivative of this thing at 9. So what are we looking for? We're looking for the limit as y approaches y naught, or 9, of the square root of y minus the square root of 9 all over y minus 9, right? That's what we're trying to solve, and we better get 1/6, otherwise we did something wrong. So this is equal to, the numerator will keep the same, that's still just the square root of y minus 3. In the denominator, this is the same thing as, we have a difference of squares, so that's the same thing as the square root of y minus 3 times the square root of y plus 3, right? Sorry, forgot my limit. The limit is y approaches 9. Okay. So we've got this thing. Top and bottom cancel out, so I'm left with, this is equal to the limit as y approaches 9 of 1 over the square root of y plus 3, which is equal to 1/6. Ta-da, it worked. Now here's where you're most likely going to get confused when you go to do these problems. You're most likely going to say, okay, when I did f prime at x naught, I got 6. So then when I do y inverse prime at x naught, I should get 1/6. Remember, it's y inverse prime at y naught. So if we look at f inverse prime at x naught, sorry, let me write my prime somehow, parentheses. F inverse prime at y naught is not the same thing as f inverse prime at x naught. That's most likely where you're going to get confused when you go to do these yourself. You're going to say, since f prime at x naught was equal to 6, then f inverse prime at x naught should equal 1/6. That is not the case. It's f inverse prime of y naught. When I plug x the function, I get y naught out. I have to plug y naught into that function to get x naught out. So we weren't talking about the slope over wherever x naught happened to be here. We were talking about the slope at y naught to get the reciprocal. Does that make sense? That's going to be the biggest gotcha. If you'll use x's and y separately, I don't think you get confused by it as much. If you keep in mind that we're talking about at a point x naught, y naught, or at a point y naught, x naught, depending on which function you want to think about in terms of. Okay, so now let's do our actual proof of the inverse function. We've got a mouthful to consume here. So let I be any neighborhood of x naught. So I is just an open interval and x naught is a point in that open interval. And let f from I to r be strictly monotone and continuous. Okay, since it's strictly monotone, then we know its inverse function is continuous. So I'm choosing that note over there. So far we now know that the inverse of f is for sure continuous. Suppose f prime of x naught exists, and that it's not equal to 0. Why don't we want the derivative to be 0? Notice, if m1 is equal to 0, then what's m2? Undefined. So that's why we're making that known. So suppose f prime of x naught, the derivative of x naught exists, and it's not equal to 0. And let j be the image of f, because we just want to write the derivative, or the domain of this function with a letter instead of saying f of I. So let j be basically the domain of our inverse function. And we're going to prove that it is differentiable at the point y naught equal to f of x naught. And that its derivative is this exact value. Mouthful, think you understand what we're trying to prove? And we know that both the functions are continuous, and we know that f is differentiable at this point, and this point isn't a 0. Okay? So we're trying to show that the derivative of this is equal to this, so let's just solve for its derivative. I don't know that we need to write out all the words with this. I can kind of explain it as I do it and just show you the math. So the limit, so we're looking for the limit as y approaches y naught of this thing. So in our numerator, what do we have? We have f inverse of y. Which one do we usually write first? For y? Minus f inverse of y naught all over. Shoot, I should have started this. First line of our proof. Let y equal f of x. Or let x equal f inverse of y, whichever way you want to think about it. Let x equal f inverse of y. Because we're going to make reference to that. Then, here's our derivative. Right? This is the exact same thing as the inverse of y is x minus the inverse of y naught is x naught all over, and I'm going to write these in terms of x. That's the same thing as f of x minus f of x naught. You with me? Let's not do the limit yet. Let's just write this is the same as this, and then I'll take my limit, that way I don't have to write over and over again.
Okay.
Did you have a question?
No.
Let's look at that. Then there. Then this is equal to this is equal to 1 over, I'm going to do, what's the best way to make intuitive what I'm doing here? I'm going to divide the numerator and the denominator by x minus x naught. So when I take the numerator and I divide it by x minus x naught, that gives me 1. And now I'm going to take the denominator and also divide it by x minus x naught. So that gives me f of x minus f of x naught all over x minus x naught.
Which one is?
So here's the big line, here's the little line.
That's what I thought.
Numerator, denominator. I times top and bottom in the denominator by 1 over x minus x naught. Or another way to say it is I divided the numerator by x minus x naught, and I divided the denominator by x minus x naught. So it's still the same value. Make sense? Okay, so now we got the algebra down. Okay, now we need to show that, notice that the limit as y approaches y naught of f inverse of y is equal to f inverse of y naught. Okay, so we know that the inverse function is continuous. How do we know that?
Because it's monotone?
F is monotone and it's on an interval. Sorry, it's on an interval and it's strictly monotone. And I said, note this was something that we proved a couple weeks ago. So we proved that if f is a function on an interval to r and it's strictly monotone, then we know its inverse function is continuous. So f is strictly monotone and it's on an interval. Therefore, f inverse is continuous. Therefore, this limit equals this. You good with that? And another way that we can say that is the limit as y approaches y naught of x is equal to x naught. Okay, so now we know that the limit as y approaches y naught is the same thing as the limit as x approaches x naught.
Wait, why do we know that?
What is f inverse of y? X. What is f inverse of y naught? X naught.
Right.
That's why I say it's going to be way helpful to keep one variable associated with one function and another associated with another function to go back and forth as needed. Okay, so now we can take the limit of this as y goes to y naught is the same thing as the limit as x goes to x naught, which is going to give us 1 over f prime, right? So then, the limit as y approaches y naught of this function, 1 over f of x minus f of x naught, all over x minus x naught, is equal to the limit as x approaches x naught of 1 over f of x minus f of x naught, all over x minus x naught, which is equal to 1 over f prime at x naught, which is what we were after.
So what did you do when you were switching your limits?
When I was going from y to x,
Yeah.
I just know what the limit of, well, notice that the limit of a quotient is the quotient of the limit, so I can split that up into the limit of 1 and the limit of this thing. Probably should have done one more step here. But I only know the limit of this if we're doing it as x approaches x naught. What's the derivative? By definition, f prime of x naught is the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught. That's the definition of the symbol. And so I can only substitute if it's written this way.
So why can you just switch from y naught to x naught?
Why couldn't I or why could I?
Why can't you?
Still not sure what you're saying.
So I'm saying right there you have the limit as y approaches y naught, and then you switch it to as x approaches x naught.
That's justified right here.
But that doesn't change anything.
Well, I need to validate that this is true. Is it true that this limit and this limit are the same thing? That's why I validate up here. The limit as y approaches y naught, here's another way to say it. As y approaches y naught, x approaches x naught.
Okay, how do we know that?
Because this is continuous. What does it mean for a function to be continuous at a point? F inverse is continuous at is continuous at y naught, if and only if the limit as y approaches y naught of f inverse of y is equal to f inverse of y naught. It's hard to say with all the inverses and naughts. In general, we write it this way. A function is continuous if and only if the limit as x approaches x naught of f of x is equal to x naught. When we defined this limit notation,
Is equal to f of x naught?
sorry, thank you. Yes. Here's another way to say it. If we have a sequence of x's that converges to x naught, then a function is continuous if and only if the image of the sequence converges to the image of x naught.
Yeah, that's right. Okay.
So, since f inverse is continuous, we know this. So we know that so then we knew this is just substitution. And that's how we go from here to here.
I don't completely understand how the limit as y goes to y naught of x equals x naught justifies your switching limits. How you go? How you use y's in one and then x in the other?
Because we're approaching the same values. This is just if this is a sequence that approaches this, and this is a sequence that approaches this. Now we did need to justify one more thing here that I forgot to justify. So we know that x is equal to x naught. The last thing that we need to validate is x is never equal to x naught as we approach it.
Right.
Because it might have accidentally hit it along the way, and that's where strictly monotone comes into play. So we're basically validating the problem is our functions could sometimes look like this. And so just because as x approaches x naught, so we'll call x naught some arbitrary point over here. Just because I know x approaches, so here's x naught, and here's y naught. So I do know as x approaches x naught, that y approaches y naught. That is true. I don't necessarily know that as y approaches y naught, x approaches x naught. Because y could be getting closer and closer to this point, which is y naught. It could be getting closer and closer to this point, which is y naught. It could be getting closer and closer to this point, which is y naught. And so it's not necessarily the case that x is approaching x naught. It is the case when you have a strictly increasing function, or a strictly decreasing function, because then the value only shows up once.
Right.
And so it is the case that, well, that's just using the fact that it's continuous. Sorry, we didn't need the monotone. The monotone gives us the continuity, and continuity gives us that, so we're actually good. No, we still need to reference that. Limit just tells us they're the same. The fact that they're increasing means if we don't use this point in the sequence, then we're guaranteed that they're never equal. And since this point is always mapped with this point, and we didn't use this point in this sequence, we didn't use this point in this sequence. So kind of using the fact that's 1-to-1, which is the same thing as, is it 1-to-1? No, that's just both continuous. But it's strictly monotone, 1-to-1. That's where we're getting 1-to-1. So I comes from strictly monotone. So we know that this is the case, and x is not equal to x naught, ever. So we never divide by 0, and we, by definition, we're dividing by f of x up there, because we're doing the limit as y approaches y naught.
Is that limit saying that y naught is equal to x naught?
Y naught is equal to x naught? No.
Well,
You're saying right here?
yeah, if you're just taking the limit as it goes to y naught, isn't it? Don't you just substitute that constant in?
Y is, it depends on how, y is some function in terms of x,
Oh, okay.
right? We wrote it backwards right there, but the other way you write that is f of x equals y. So they're just functions in terms of each other. You can think about x as a function in terms of y, or y as a function in terms of x. So this isn't the whole function. This is a stand-in for some function. Because you might think, this only works for you since we haven't done the chain rule yet, but to answer your question, when I do the derivative of something like x squared, what is it really? It's really 2x dx, depending on what x is, because x could be a function in terms of another variable.
Right.
Right.
Okay.
Anyways. Any other questions on that?
I think it, I mean,
And then we have a nice little corollary that follows from this. Almost says the exact same thing. So now we're just going to say that it's differentiable on an entire interval. So let f be a function from some interval, and this interval is, anytime I use the I, that's going to be a neighborhood of x naught, so we're going to assume x naught's pointing there. So let f be a function from some neighborhood around x naught to r, be differentiable and strictly monotone such that its derivative is never 0. Then the inverse function is differentiable, and the inverse function at any point x naught in I is equal to this. So now we're just saying for a whole domain, for a whole interval. Now, you might look at this and say, is that drastically different from what we have up there? But it's really saying the same thing, it's just in terms of a different variable. So let me rewrite this out. So we have f inverse prime at x naught. What does that mean? That means that f of y is equal to x, because we're saying f inverse of x is equal to y. They just decide to write the inverse function in terms of x. If you write the inverse function in terms of x, then write the initial function in terms of y. So that's another thing that he did in his corollary. So instead of doing it in terms of y, he's writing the function in terms of x. It doesn't matter what we use as our variable. If you use x's for one function, just use y's for the other, and I think it will help you clear yourself out. So now, what is he saying? He's saying this is equal to 1 over f prime of, what is f inverse of x naught? That's just y naught. And notice the similarities between that and that. So it's not really saying anything different. He's just writing this function in terms of different variables.
And what's the point of it?
Well, sometimes your variables might be, sometimes you might be given the inverse function in terms of x.
So, you can still plug it in that way, can't you?
You can still plug it in this way, if you want, but don't get confused between your x's and your y's.
Yeah.
Yeah. So, yeah, that's what I'm saying. This and this are saying the exact same thing. It's just a relabeling of the variables.
Okay.
Yep, nothing big. So, let's prove it. Observe that differentiability implies continuity, so f is continuous. So it was given to us that f is differentiable. Since f is differentiable, we know it's continuous. And so now we can just use the function up there. So let x naught be any point in the domain of the inverse function, and define y naught to be f inverse of x naught. Then f inverse prime at x naught is the exact same thing as 1 over f prime of y naught. That's just using what we have up there, just variable swapping, and then here's writing it the way that the author had it. Y naught, that's the same thing as that. So just a simple corollary. Anything weird? Just need to look at it.
Yeah, I'm just trying to it's hard to keep track of everything that's going on.
Yeah, going back and forth between the inverses and the regular functions when you don't, because you're so used to consistently doing y equals f of x,
Yeah.
and so anytime we upset that paradigm, then it throws you for a loop, which is why inverses are always a little bit tricky to deal with in proofs. It's kind of like the absolute value function. You're so used to that when you take absolute values, you don't get negative values. But if I tell you absolute value of a, where a is negative, is equal to negative a, the first time you see that, you're like, no, that's not possible what you have written there. Similar type of thing. So yeah, keep your x's and your y's straight, and I think you'll be fine in your proofs. Don't try rewriting a function that's given to you in terms of x, in terms of y, and then resolving it. I think you'll end up making a mess and confusing yourself. Because that's typically how they tell you to find inverse functions, right?
Yeah.
If you were in like a college algebra class, they say, what's the inverse of f of x is equal to 2x plus 1? They tell you, right, y equals 2x plus 1, and then they tell you, okay, now write it x equals 2y plus 1, and then write it in terms of y, so then you get y is equal to x minus 1 over 2. And there's your inverse function. But now your x here and your x here do not mean the same thing.
Right.
So this is how you did it in college algebra course. Now that's going to become a complete nightmare for you inside of a proof, because then your x is no longer consistent. So if you just write the inverse function of this, is x is equal to y minus 1 over 2. Now your x's and y's mean the exact same thing. And you can always do your substitutions however you need. Everything's fine, everything's consistent. It's just that now we have f inverse written in terms of y is equal to y minus 1 over 2. So that's the difference from what you're used to. And it's far better to do it this way, because then your names are consistent. And you don't have to remember which function a particular x was associated with. So let's do an example. Well, we're going to prove something, but we're going to prove something now using this to help us see it in a more concrete way. And I'll show you how I make explicit my functions to help me keep track in my head as I'm proving this. So I'll let n be any natural number and let g be a function from the positive real numbers to the real numbers by g of x is equal to x to the 1 over n. I'm going to prove that g prime of x is equal to 1 over n times x to the 1 over n minus 1. So that the same rule that we learned with when you have x to an integer applies when you have x to 1 over some positive number. And then we'll do rational numbers very, very last. But you understand what we're trying to prove?
It's basically the power rule.
Yeah, it's almost identical to the power rules. The power rule, but now we're using a number like that. So instead of the derivative of x to the 9, you already knew that that was equal to, so when I do the derivative of this, that prime, that's 9x to the 8. Well, now if I have x to the 1 over 9, and I'm trying to do its derivative, we're going to see that that's 1 over 9 times x to the negative 8 ninths. Or 1 over 9 minus 1, which is that. There's the derivative. That's what we're proving. So you understand what we're trying to prove? Yeah? Yeah. Okay. So let's prove it. So let f be some function from r to r by f of x is equal to x to the n. And observe that f inverse of x is equal to g of x. Oh, I didn't keep consistent on my variables. Oh, that's because I was going to plug it in exactly how he had it here and here. Okay. So, this is what I'm trying to find the derivative of. I'm just calling that f inverse of this function. You with me? I'm just creating a new function, f of x, and I'm defining it in terms of g of x. So f of x is equal to x to the n. Now f inverse of x is equal to g of x. Because g of x is equal to, sorry, it's up here, g of x is equal to this. What is this by definition? It's the inverse of this.
Okay.
You with me?
Yeah.
Because I'm just going to use this exact theorem right here. So I rewrote it in terms of f so that you can see exactly how I'm using it. Now I could have left my f in terms of y and then my f inverse in terms of x, but I think we're fine. So you're good with up to here, just what I called my functions. Nothing weird. Okay, observe that f prime of x is equal to n times x to the n minus 1. So I'm finding its derivative. Why? Because its derivative shows up right there. Or right there. Sorry, that's the formula we're using. So we now have its derivative. Okay, so now g prime of x.
Wait, you did that by just substituting from that corollary?
I haven't used the corollary yet. I'm just motivating why out of the blue I found the derivative of f.
Yeah, how did you do that?
We already know that the derivative of x to the n is n times x to the n minus 1.
Right.
So I'm just writing out all my terms explicitly. Now comes the actual proof. So then, g prime of x is equal to f inverse inverse prime at x, by definition of how I define my x, right? Or by definition of how I define my f. You with me up to here? How g prime of x and the prime of this thing are the same thing, since g and f inverse are the same. G and f inverse are the same.
Yeah.
No?
Oh, okay, yeah.
Okay. So g prime of x is the same thing as f inverse prime of x, which now using that corollary we know is f prime of f inverse of x, or f prime of the y associated with x. Not swapping the variable names, but same thing. Don't get confused that this is just giving me the y that went to that x, right? So here's where we use the corollary. Now I know what f prime of anything is. It's n times that thing to the n minus 1. F prime of anything is equal to n times that thing to the power of n minus 1. F prime of anything is equal to n times that thing to the power of n minus 1. And what is that thing? X to the 1 over n. That is f inverse of x. You with me? Okay. So now I have that. Now the rest is just algebra simplifying. That's all my substitutions. So let's see what I'm doing first. I'm distributing the 1 over n. Remember, when you have exponents like this, you multiply the exponent. What's 1 over n times n? 1. What's 1 over n times negative 1? Negative 1 over n. This is an exponent. This is an exponent.
Yeah.
Multiplying the exponents, you get that. Right?
Okay.
Okay. So I still have my 1 over n. I just pulled that out. That's just going to be a constant. Times x to the 1 minus 1 over n. Now if I want to move my term to the numerator, my exponent becomes negative. So I'm going to write my x in the numerator, which is going to make my 1 a negative 1, and my 1 over n a positive 1 over n. So just make the exponent negative. Now reorder the exponent. You follow that?
Yeah.
And that's it. I mean, honestly, I think the hardest part of this is just getting set up to right here. And then from there on out, everything just follows. It's just plugging in terms after that. Good?
Yeah.
Ready to move on? Alright. Next proof. Let's see what we're proving now. Oh, now we're proving the chain rule. So that was everything with inverse functions. Now we're going to do how do we take the derivative of function composition. And we'll do an example of this to see that it works, and then we'll actually prove it. So let's come up with a function for f of x. We'll say f of x is equal to x squared, and we'll say g of x is equal to x plus 2. So what are we saying here? We're saying g composed with f of x prime is equal to let's write out the terms up here. What is f prime of x squared? What's f prime of x, I mean?
Just 2x.
2x. And we need a g prime. What's g prime? Since g comes first, let's flip these. Let's make this one x plus 2, and let's make the g x squared. So now this is 2x, and what's f prime of x? 1. Okay, so now we're saying g after f prime of x is equal to g prime of f of x, not What's f of x naught?
X naught plus 2.
It's just 2 in this case, right?
Right. Wait.
No. 4. No. X naught plus 2. What are we doing? At x naught, okay. We can just do that at x. We're way overthinking. Okay. So we're doing this formula. So I'm plugging in f of x into g prime of x, so x plus 2 in here, times f prime of x is just 1, so that comes out to 2x plus 2. I'm going to pick different ones. Sorry, I should have done this better. Pick ones where the derivative is more obvious. So let's make this one something like x squared plus 4, and we'll make this one something like x cubed minus 2. Okay, now let's do it again. So we're looking for g composed with f prime of x. That's equal to g prime of x. Let's find g prime of x really quick. G prime of x is equal to 3x squared, and f prime of x is equal to 2x. Okay.
Okay. How are we finding these? Because I feel like that's where I'm getting on these.
Okay. So if f of x is equal to x squared plus 4, what's f prime of x? What's the derivative of x squared?
It would be 2x.
2 times x to the 1. What's the derivative of 4? There's 2 ways that you could quickly think about it. So the first one is, what does the function 4 look like?
It's a straight line.
What's the slope of a straight line?
0.
There's one way to think about it. Another way that we can think about 4 is the same thing as 4 times 1. What's the derivative of this?
0.
0 times x to the negative 1, or 0, times the 4, is still 0. So whatever helps you remember it better, but the derivative of a constant is just 0. Okay. So, and since a derivative is just a limit, the limit of the sum is the sum of the limits. So I can take the derivative of that plus the derivative of that. I don't need to think about the derivative of the whole thing in one go. So the derivative of that is equal to that, right? Now back to this one. What's the derivative of x cubed?
It's 2x squared.
3x squared. Bring down the 3 and subtract 1 from your exponent.
Right.
The power rule. And what's the derivative of negative 2?
0.
0. It's constant. Okay. So now, using this formula, we get g prime. What's g prime? That's 3 of whatever you've got squared. G prime of f of x. F of x is x squared plus 4. Right? Times f prime of x. F prime of x is just 2x.
So
You follow substitution there?
we're trying to I'm sorry, I need to go back to what we're proving in the first place.
We're not proving anything yet. We're doing an example of this.
Oh.
So I'm going to find the derivative of this using this formula, and then I'm going to take the derivative of this using what we know to see that they're the same thing.
Okay.
So this is just using the formula. So now when we expand this out, let's see, what are we going to get? We're going to get 3x to the 4 plus, what's 8 times 3? 24x squared plus 16 times 3, 48. But now we need to multiply all that by 2x. Sorry, I was just squaring that out and multiplying by 3 as I went. Should have specified that. Which is equal to, we're going to get 6x to the 5 plus 48x squared plus 96x.
Shouldn't that be x cubed?
Yeah.
X cubed, thank you. Okay, so that was one way of doing it. Now let's do this problem the way that we already know how to do this problem. So g composed with f of x, what is that? That is, plug in f of x to g, what do we get? We get x squared plus 4 cubed minus 2. We plugged in that for x in this equation, right? So that's just rewriting g composed with f of x, and we need to find the derivative of this thing. But first let's expand this thing. So, in case it was confusing what I was saying, this is the same thing as g of f of x. That's what this is. So now let's expand it out. Okay, we're going to have x squared times x squared times x squared 3 times, so that's going to give us a 6, plus 3 times x to the 4 times 4 plus 3 times x squared times 16 plus 64. I hate having this desk here. It's obnoxious. Minus 2. Right?
Yeah.
So that is equal to, come down to this line, we have x to the 6 plus 12x to the 4 plus 48x squared plus 62. Okay, now let's take the derivative of that thing and see what we get.
Where did you get 12x? 4?
We have 3x to the 4 times 4.
Okay, right.
So now when we take the derivative of this, we're going to get 6x to the 5 plus, maybe I should have you guys do it. What's the derivative of this term?
48x to the 3.
48x to the 3
So
plus,
when you're taking the derivative, you just take the derivative of each term separately.
yeah, because a derivative is just a limit, and the limit of the sums is the sum of the limits. I wonder how heavy this is. More wriggly than I thought. Anyways, so the derivative of this term,
96 times 6.
yeah, just bring down the 2. So 2 times 48 is 96, minus 1 from the exponent. 96x, what's the derivative of 62?
0.
0, because it's just a constant. So that's what we got. Let's see what we got here. Yep. Same thing. Okay, so it appears the rule works. Now we'll prove it. Unless there's any questions on anything we did here? Good? Alright. So now, let's prove the rule. So we're looking for the limit as x approaches x naught of, and rather than writing it this way, I'm going to write g of f of x naught minus g of, do we do the x naught first or the x first? X. Over g of f of x naught all over x minus x naught. Right? That's what we're trying to solve, and we're trying to show that this is equal to this thing. With me so far?
Yeah.
Just plugging in? Okay. So now, this is equal to the limit as x approaches x naught. I'm going to multiply top and bottom of this by the same thing, and we'll write it a funny way. So, should have written up here, let y equal f of x. Okay, so I want to use y's rather than keeping my s in there to help us see it better. So let y equal f of x. So now I'm going to rewrite this with y in it. So g of y minus g of y naught all over x minus x naught. And I told you I was going to times this top and bottom by 1. And the 1 I'm going to multiply top and bottom by is f of x minus f of x naught all over y minus y naught. You see how that's just 1? F of x is y, and f of x naught is y naught. Right? So that's just 1, so we've just taken this and multiplied it by 1, we haven't changed anything. Good? So now this is equal to, and I'm going to switch the order I write my denominators in. So I'm going to associate this denominator with this term and this denominator with this term. Still the same thing since we're multiplying fractions, right? Follow that algebra? So this is equal to the limit as x approaches x naught of g of y minus g of y naught all over y minus y naught. And I'm actually going to split this up into two limits because the limit of a product is a product of the limits. Just like we can hurry up and evaluate one of these things. F of x minus f of x naught all over x minus x naught. Right? Nothing weird? All I did was swap the order I wrote my denominators in and use the fact that the limit of a product is a product of the limits. Now I know how to evaluate this limit, right? What's this limit?
F prime of x naught.
Yeah, this is just f prime of x naught, which gives us, if you look at what we're trying to prove, okay, we got that thing right there.
Why?
That's the definition of f prime of x naught,
Yeah, that's
right?
Right.
So now, this is equal to the limit as x approaches x naught of g of y minus g of y naught all over y minus y naught times, and then now this is just a constant, f prime of x naught. F prime of x naught, that's just a number, right? So all that remains to do is to figure out this limit, right? Now, notice that as, so notice that the limit as x approaches x naught of f of x is equal to f of x naught, or that's the same thing as, if you want to see it this way, the limit as x approaches x naught of y is equal to y naught. How do we know that? We know that f is a differentiable function, and so if it's differentiable, it's continuous. At that point, we know it's differentiable at x naught, therefore it's continuous at x naught. So that's how we know this. You with me? So now, we want to, the limit as x approaches x naught is the same thing as the limit as y approaches y naught of g of y minus g of y naught all over y minus y naught. This is what we want to evaluate. Now here's where we have to be careful, because we don't have a strictly monotone function like we had over here. And it is actually possible that somewhere along the way, this was 0. As x approaches x naught, just because x is never equal to x naught, we do not know that y is never equal to y naught. Because since it's not a strictly monotone function, then the function could be increasing and decreasing. So if I have x naught here, if this is my point, x naught, y naught, then it is not the case that, well, how can I say this? The same y naught value shows up in a lot of different places. So it's possible when I take my sequence of x's converging to x naught here, that one of those x's actually had a y associated with it that makes this denominator 0. So it's possible when I go to do this limit that that denominator is actually 0. It wasn't possible over here because we always had a strictly increasing function. And so we knew that the only place where y was equal to y naught was at x naught. So when I look at this function, if we draw it on a coordinate system, I know any time, if this is y naught, I know that the only place where y is equal to y naught is at x naught. So I knew over here that as y approaches y naught, we never use y naught in the sequence. Because by definition we never used, oh sorry, we had it backwards here. We were using the fact that y approaches y naught to say x approaches x naught. But same thing, our x's here are the output of our function and the y's are the input. But I know that it's going to get confusing going back and forth between these x's and y's, so I'll stick with over here. I know by definition of the limit as x approaches x naught, that is a sequence of x's that gets closer and closer to x naught that never uses x naught. And I need that to create a sequence of y's that get closer and closer to y naught but never actually use y naught. When we have a strictly increasing function, that's easy to do. When we don't know anything about our function, then we have a problem that this can sometimes be 0. Do you see the problem I'm pointing out? So our fix for this is to create what we call an auxiliary function, but I don't want to show you the fix until we just evaluate it intuitively, and then we'll go back and do the fix, because understanding it without the fix is good enough, and then the fix is just taking care of making sure we never divide by 0. So we'll come back in and put in that fix, but here's how we'll do it. So let's assume for now that we can rewrite this as the limit as y approaches y naught of f prime of x naught. So let's assume for a second that this is never 0. Now we can evaluate this limit, right?
Right.
Yeah, well,
If y is never equal to y naught, then now we can evaluate this limit.
yeah, but we'll pause that fixing our problem.
We haven't fixed it yet. I'm saying assume that we have a solution to fix the problem, or that for some reason we don't need to worry about the problem. Will you help me just move this desk? This is going to drag me nuts. Just shove it back a foot. Because I think we're going to have to kind of lift and slide without actually lifting. That should be dead things.
Okay.
Okay. So let's assume for a second that y is never equal to y naught. Then what would this limit be?
Just g prime of y naught.
That's just g prime of y naught. So then we just have g prime of y naught times f prime of x naught, which is the same thing as g prime of f of x naught times f prime of x naught, which is what we're after.
Right.
So just following through at this proof should be intuitive that, yeah, it's going to lead to this. Now we need to deal with our one technicality, h of x. Because when we look at this function, it's possible that if we were to graph this whole function, it's possible that it has a hole at y equal to y naught. And so we basically need to fill in the hole. That's essentially what our auxiliary function is going to do. So we're going to create an auxiliary function, hx.
Well,
Yeah.
I'm a little confused. I thought the problem was that y could be equal to y naught, not that
Right.
there just wasn't a y naught.
Y could be equal to y naught. And so when you graph this whole thing as a function, that essentially creates a hole at that point. That's just intuition.
Oh, right.
But we'll still solve it by making sure that's not possible. So we'll create h of y, and we'll define it to be so that it's equal to g of y minus g of y naught over y minus y naught for y not equal to y naught. And we'll define it to just be g prime of y naught when y is equal to y naught. Now remember, g is differentiable at f of x naught. Let's see, where did we say that? Let f be differentiable at and g differentiable at y naught equal to f of x naught. So this is just a number. You with me that that's just a number? And we're given that that's just a number?
Where are you giving that?
So, and g is a function that is differentiable at y naught. So I know that g prime at y naught is a number. It's differentiable there. That limit exists, and it's just some number. Here's our symbol for what that number is. So now we have h of y, and so now what we're going to look at is the limit as y approaches y naught of h of y times f prime of x naught, and this is going to end up equaling this. Because now we have to handle two cases. We handle when h of y is this, in which case it is, we just barely showed that up here, and we handle when h of y is this, then it is because we're just substituting that in directly. So since no matter what, we always get that this limit is equal to g prime of y naught times f prime of x naught, then we're good. Notice that this function always gives the same value as this function. Except for now it's defined at y.
I'm still trying to understand how this whole auxiliary function is a valid thing to do
Yeah.
in this proof.
How it's a valid thing to do.
You're just like,
Yeah.
oh.
We're
for this
filling
one
in
case
a hole because it doesn't change the limits.
And it feels like you're saying, okay, there's a problem, so we're just gonna say that's not a problem anymore.
If you were to graph this function, then, and when I say graph this function, I mean this whole quotient.
Okay.
If you were to graph that whole function, then whatever it looked like, what we're going to have is potentially a hole somewhere.
Right.
And all we did is we filled in that hole, and so all our limits across this function are still the same thing. Now we just don't have to worry about the technicality of dealing with the hole. Because remember, even if I have a hole in the function, the limit at that point is still the exact same thing. Whether the function is defined at that point or not, when you have a hole there, the limit's still the same thing. Filling it in with the hole, with the same limit value, just makes so I don't have to deal with the technicality of there being a hole there. When we're taking the limit, it doesn't change anything. The values are still the same.
So how does this, how again does this help us in finishing off the proof?
So that we don't accidentally divide by 0. All we're saying is, in the case where we might have accidentally divided by 0, rather than saying our function's undefined at that point, we're just going to call it this number. And when it is defined, we're going to call it this number. So then when you take the limit of this thing, anytime it's this, what's the limit of this? It's g prime of y naught. What's the limit of this thing when y is equal to y naught? Well, that's just the limit of a constant, which is just that constant. So in either case, we get this. So this limit, the limit as y approaches y naught of h of y exists and is that thing. And its limit is the same thing as that thing's limit.
So just to clarify, you're saying that we can use h of y because the limits of h and y and the function that you have above it are the same, so we can use h of y to come up with the...
Yeah, they evaluate to the same limit. We couldn't have chosen this to be any different number and had it still work. Because we chose that number specifically to be the point that fills in the hole. But, so that's why I'm saying it's just a technicality to deal with. We don't ever want to divide by 0. I mean, another way that we could have done this proof, it just would have been far more tedious, is to say, now go look at the sequence of y and remove the points in y that happen to be y naught, and argue that the sequence still converges the same way that it did before, and it would have been a similar way to do it. The same way that you could argue a sequence converges to the same thing it converges to, even if you remove a finite number of terms, is a similar argument to saying the limit of this when you fill in that point and when you don't fill in the point are still the same.
Yeah, the second part makes sense more to me than this does. But yeah, I understand now.
That would just be way harder to deal with because we'd have to rewrite these limits in terms of sequence limits, then argue removing the points, then convert back to these limits, and then we would go. But if you understand just this, then I think you're good for understanding the function composition.
I feel like I get the reason why we're doing it, like I understand like the algebra there and everything. I'm not exactly, I feel like there's something I'm missing, like, I don't feel like,
Well, you can also always read the way that the author does the proof and read his explanation.
okay,
And that could give you another take on it. Because there might be something that some subtle detail that I'm saying wrong or that I'm not clarifying enough. I don't know. But yeah, the whole point of the auxiliary function is just make sure we're not accidentally dividing by zero. Get rid of the y's that make us divide by zero would be an equivalent way of doing it. Make sure that when we're talking about a sequence of terms, we draw some function that has repeating values. So I've got some function like this, and I've got my x's converging to some x naught, so here's x naught. As I've got x's converging to x naught, ultimately what would it be doing? It'd be saying if any of these x's that are in the sequence converging to x naught accidentally used a y value that's equal to y naught, pull those terms out of the sequence and create a subsequence that way. Would have been another way that we can do the same thing.
and we're doing this so that our sequence is like.
We just want, so that when we look at y minus y naught, that's never zero. That's all we need. And so we just need to basically either remove those points here and see that's still the same, or when we do divide by zero, fill in those points with an auxiliary function so that we don't have to worry about it anymore. It's two logically equivalent ideas. It's just this first way would be a lot harder. But that's the reason that we have the problem. But it's a corner case. The gist of the proof, without that auxiliary function, is what's important for you to know. Good? Okay, so the last thing that we need to prove now is, we'll just get rid of some space here. Last thing that we need to prove is basically prove that if f from 0 to infinity to r by f of x is equal to x to the r for r in q, for some rational number q, proof if this. If f is that way, comma, then f prime of x is equal to r times x to the r minus 1. So we've proven it for integers, now we've proven it for 1 over a natural number, and we're going to combine it. Now we're going to prove it for rational numbers in general. Obviously we're going to use function composition on 1 over n for the denominator and an integer for the numerator. Right? So 1, we'll just write this out. Let f be a function from 0 to infinity, from the positive real numbers to r by f of x equal to x to the r for some r in q. 2. Then there exists some natural number n and some integer m such that r is equal to m over n. Remember that? R can always be expressed as an integer over a natural, so we can guarantee the denominator is never negative, in other words, when we write a natural for a rational. So 3. Maybe we'll name the other function so that we can see the composition explicitly. So let's see, we already used f, so let g, and we can say from 0, infinity to r, by g of x is equal to, let's see, we'll do g is equal to x to the m Let's see, that one can just be r to r. We don't need to worry about restricting the domain on that one. Do we? No. And let h from h is going to be the inverse now, so that's one we're removing the restricted domain. 0 to infinity to r by h of x is equal to x to the 1 over n. Then f of x is equal to, doesn't matter which order we do this in, we'll say h of g of x. You follow that? So I just rewrote f of x as a composition of two functions. And two functions that we know how to differentiate, which is the important point. You did?
Why are we doing h of g of x instead of g of h of x?
H is the one with the restricted domain. I know that the image of h is a subset of the domain of g, so I know that this way is always defined. The other way might not have been, I mean, we know it is defined the other way, but there could have been, no, I don't know if we know it is the other way. We would have had to restrict the domain on g if we wanted to do it the other way. But this way is for sure defined, right?
I don't think we would have had to restrict the domain.
On g,
Yeah, h of x would be all the real numbers, and then the domain of g is.
h can't take a negative number. It's possible for g to spit out a negative number. Right? Because n
Oh.
could be cubed.
Well, the final function has a domain of 0 to infinity.
Oh yeah, so we want,
So,
oh, f wouldn't have been equal to it unless we restricted the domain of g. So yeah. So if we restricted the domain of g, then we still could have done it, and f would, because it shouldn't matter down here which way we do it. But with the way I have it defined now, this is true.
okay.
But yeah, we could have changed the order of those, and it wouldn't matter. We just would have had to write that as 0 to infinity, but this equality would have still been true. Okay, so now we have this, so 5, now we just need to take the derivative. So then f prime of x is equal to h prime of g of x times g prime of x. That's using, I don't know if I told you the name of that, but theorem 4.14, that's called the chain rule. And we'll say it a lot.
Why?
The chain rule. And the way we read it, should have said this too. We say that when you're taking the derivative of a composition of functions, let's look at it this way. When we're taking the derivative of this, we say you do the derivative of the outside multiplied by the derivative of the inside. Is how we typically summarize the chain rule. But
Okay.
yeah, the reason we call it the chain rule is because this could have been a long string of function, inside function, inside function, inside function, and as you differentiate it, you get this big chain of derivatives. So this is just for 2D, but okay. So now we know how to find all these things, right? What is h prime? So h prime is 1 over n times whatever we have, g of x, in this case g of x is x to the n, to the power of 1 over n minus 1. So that's doing this term. You with me on that?
That's just using the power rule.
Yeah. Just bringing 1 to the n down and making that exponent 1 to the n minus 1.
Okay.
So that's h prime of g of x, and so plugging in g of x for x as well. So that's this term, times g prime of x is just m times x to the n minus 1. Right? So now, it's just algebra. So now this is equal to, I'm going to combine my m and my n, m over n times, distribute the m across both those, we get x to the m over n minus m, multiplying that by m for my exponent there. And we have this times x to the m minus 1, right?
Yeah.
So then, that is equal to m over n times,
Wait. Isn't that, why is that x to the n minus 1 instead of just x to the n?
I did the derivative of x to the n. The derivative of x to the 10 is equal to 10 times x to the 10 minus 1, 9.
That's right.
Power rule. Good? Okay. So now, and then when you multiply terms, you add exponents. So I have m over n minus m plus m minus 1, which leaves me x to the m over n minus 1. And now if you write that in terms of r, it's just r times x to the r minus 1. And we're done. Any questions? And this is what we now call the power rule, because this handles all cases. Well, all rational cases. We didn't prove it for real numbers, just rationals.
Yes, did we end up proving it for real numbers?
I'm not sure you can prove it for
Yeah.
real numbers. Have to think of a counter. Maybe it is true for real numbers in general. I don't know. We'll see. Any other questions? Okay, and that's it for this material. You have the rest of the class to start your homework. I'll start uploading the lecture.